This example comes out of section 2.2, the power rule. As we went through some of the examples in 2.1, first principles, and we started finding some derivatives. One of the first ones we found was that the derivative of f of x equals x squared. And when we found the derivative of that, we found that the answer was 2x. And I won't rehash all the limit as h goes to 0 business right here. But we also found that if the function was x cubed, went through the same h goes to 0 business and steps, and we found out that the answer to that was 3x squared. X to the fourth in the exercises, and you find out that the derivative is 4x cubed. There's no accident that if you look closely, you can find a pattern here. And that pattern basically will describe as what's called the power rule. And the power rule basically states that if you've got a function that's in this format, where you've got f of x equals x to the n, so if that's the case, and as long, for now, we're going to stick with positive integers. If n, so if n, another way of saying that is a whole number, but if n is a positive integer, meaning no decimals, no fractions, then f prime of x is going to be bring the number out front and reduce your exponent by 1. As you see, works for all the ones up above. In Leibniz notation, the other notation, the derivative of x to the n by dx is equal to n times x to the n minus 1. So, one thing I should also mention at this point is that if your function is a constant, so if f of x equals c, so f of x equals 5 or f of x equals negative 2 or whatever, if you're looking for the derivative of that, you just get 0. If you think about that as slope of a tangent line, whether I have a horizontal line here or somewhere else, the tangent always has a slope of 0, and so you have yourself a derivative equal to 0. That becomes useful when we start to do more complicated examples later on, but let's do a couple of simple examples. If I have f of x equals x to the 12, and I say what's the derivative, it just becomes 12x to the 11. So the shortcut is far, 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 far faster than if you're asked to do that by first principles, because as you can imagine, x to the 12th is a handful to deal with. It turns out that we can actually extend this rule, the power rule, to work for n as an element of all real numbers. It's a little harder to prove. If you're looking for a proof, there is a proof in the appendix of your book that will show you how to do this. I'm not going to ask you to prove the power rule, and I'm assuming any calculus prof that does will tell you that they're going to do it. Basically, it turns into just a fancy factoring proof, that one. But it turns out that this power rule actually does work as long as n is any real number. The power rule works. So let's take a look at a couple of those type of examples. So if I have, y equals 1 over x to the 4, and I say what's the derivative of that? Just use the other notation. First of all, you could write this as x to the negative 4. So the derivative is negative 4x to the negative 5. Bring the power out front, reduce your exponent by 1. So if I had then y equals the square root of x, then the derivative, maybe this time I use y prime, is going to be what? Well, square root of x is x to the 1/2, so I could say this is 1/2 x to the negative 1/2. And that's a perfectly good answer. Sometimes you'll see that written as 1 over 2 root x, which is more likely what you would find if you did it with first principles. You'd come up with an equation that looks like that. So the power rule is a clear and obvious shortcut compared to doing things with first principles.